Okay, so today we are going to talk about graphing higher order polynomials. And to do this, I'd like to start by thinking about what we already know. So we're going to think about the quadratic function f of x equals x squared plus 3x plus 2. And let's think about these questions. These are the kinds of questions we're going to be asked with respect to higher order polynomials. But I think it will make more sense if we apply them to something that's more familiar first. So we've discussed quadratic functions, and so that's what we're looking at. F of x equals x squared plus 3x plus 2. So if I identify the degree of the polynomial, that's the highest power. So when I write a polynomial, I generally write it in descending order of the exponents. So 2, the exponent here would be 1, and then there's no exponent on 2. So the degree in this case is 2. So what is the sign of the lead coefficient? The lead coefficient is the number that appears in front of that lead term that I pulled the degree from. So since nothing is written there, it's always understood to be a 1, right? So in this case, there's a positive 1. So what is the sign of the least coefficient, the lead coefficient? It's positive. And specifically, it's a positive 1. So find the zeros and their multiplicities. Okay, so for part C, the zeros and their multiplicities. 0 is another word for, sometimes they're referred to as roots. Sometimes they're referred to as the x-intercepts. And sometimes we refer to them as the solutions to the quadratic when set equal to 0. So to find the zeros, I would take my quadratic, my polynomial, x squared plus 3x plus 2, and set it equal to 0 and solve for x. Those x values are my zeros, or my roots, my x-intercepts, the solutions to this equation. Okay, so to solve this quadratic, I'm going to factor it. So I want two numbers that multiply to 2 and add to 3. So I'll use 2 and 1. And then I'll set each factor equal to 0 and solve. So x is equal to -2 and x is equal to -1. So the zeros of my quadratic are x equals -2 and x equals -1. So now this idea of multiplicities. Multiplicity just means how many times do those zeros occur. So because I just had one factor of x plus 2 and one factor of x plus 1. And so when I found my solutions, I had x equals 2 occurring once and x equals 1 occurring once. So the multiplicity of each of these zeros is 1. So now find the x and y intercepts. Okay, so I just found the x-intercepts. Since my zeros are -2 and -1, then the x-intercepts are -2, 0 and -1, 0. And remember how to find a y-intercept. To find a y-intercept, I replace x with 0. So in this case, I would be finding f of 0, or 0 squared plus 3 times 0 plus 2. So 0 plus 0 plus 2 equals 2. So my y-intercept is 0, 2. All right, so now let's think about what this graph is going to look like. All right, if my x-intercepts are at -2 and -1, I'll plot those. My y-intercept as at 2. So we haven't found the vertex. We certainly could. I'm not going to take the time to do that right now. So I don't know exactly how far down the vertex is at this point, but I can get a general shape of the graph because I know it's a parabola. I know it's going to look something like this. And that's all we really need to focus on for this particular section when we start to look at some of the other polynomials. So this is in general what it looks like. And what that enables me to do is consider what we call end behavior. So end behavior describes what's happening at the ends of the graph. So by the ends of the graph, I mean what is going on as the values of x get larger and larger and larger. So as we go to the right on the x-axis, what is happening to the graph? It's going up. And so the language that you'll see in the homework problems will be to the right, the graph rises. And then when I look to the left, so as x gets smaller and smaller, again, the end points up. So we would say the graph rises. Now, another more formal way to say this, and something that you'll want to get used to seeing in calculus, is for this first part. Oh, what did I do here? There we go. Let's put that back. So for this first part, to the right, the graph rises. We would say as x approaches infinity. So as I go to the right towards infinity on the x-axis, the graph, the output, or f of x, approaches positive infinity, meaning it is rising. And then as x approaches negative infinity, meaning as we look to the left towards negative infinity, f of x, the outputs, also rise, meaning approach positive infinity. Identify the number of turning points. So turning points are your local max and min, or absolute max and min in this case. So it's when the graph changes from decreasing to increasing, or from increasing to decreasing. So we have one turning point in this case, and that would be right here. So let's think about what we just discussed, but with what we would consider a higher order polynomial. So f of x equals 7x cubed times x plus 1 squared times x minus 1. So notice, I want to identify the degree of this polynomial, but before I can do that, I need to know what this would look like if it was completely multiplied out. I don't want to take the time to multiply the whole thing out, but I want to think about what that lead term would be. So if you think about it, x plus 1 squared is x plus 1 times itself, right? So when I FOIL that out, that lead term would be an x squared. So basically an x squared would be the lead term coming from that factor. X minus 1, the lead term would just be an x. So what I'm going to visualize multiplying out is, again, this front factor, 7x cubed, times x squared times x, which would be 7x to the 3 plus 2 is 5 plus 1 is 6 to the 6th power. This would be the lead term if I took the time to multiply this whole thing out, which I don't need to do. I really just need to know what that lead term is. So now I can identify the degree of the polynomial, and the degree of the polynomial is 6. What is the sign of the lead coefficient? The lead coefficient would be a positive 7, so a positive is the sign. Find the zeros and their multiplicities. So, like we looked at with the quadratic, the first thing we did to find the zeros is we factored the quadratic. Notice this function is already given to me completely factored. So when I go to find the zeros, I want to think about it again in its factored form. So 7x cubed, if I have x plus 1 squared, just like I looked at above, technically that's x plus 1 times itself. And then I have that x minus 1 factor. So this would be completely factored. Set equal to 0. Then we set each factor equal to 0 to find these values of x. Okay, so I would divide both sides by 7. So x cubed is equal to 0. So x is equal to 0. This would give me x is equal to negative 1. So would this. And this would give me x is equal to positive 1. Okay, so now let's talk multiplicity. Multiplicity, again, just means how many times each 0 occurs. So notice with this x minus 1, see how I have it written here twice? It's because the factor, the original factor, was squared. So I actually have two x plus 1 factors, which gives me x equals 1, negative 1, excuse me, twice. So the 0, x equals negative 1, has a multiplicity of 2. The 0, x equals 1, has a multiplicity of 1. Now when I look at the 0, again, technically that was an x cubed, and that exponent is really what determines the multiplicity. So x equals 0 has a multiplicity of 3. So when I'm looking at functions like this, I can determine the multiplicity by looking at the exponent associated with the factor that produces that 0. So to answer part C, I have 3 zeros, 1, 2, 3, and then those are the respective multiplicities. So find the x and y intercepts. So the x-intercepts are the zeros. So I've already found the x-intercepts. The x-intercepts are negative 1, 0, 1, 0, and 0, 0. Remember, the y-intercepts are replacing x with 0. So in this case, we would have 7 times 0 cubed times 0 plus 1 squared times 0 minus 1. So this would be 0 times 1 times negative 1, which is 0. So again, I already have that 0, 0 intercept. Okay, so now we would come to sketching the graph. So when I sketch the graph, I would plot the intercepts. So I have negative 1, 1, and 0. So these are the intercepts. Okay, so now I need to determine what goes on at these intercepts. Does the function cross? Does it touch and go back in the same direction? What is the end behavior of the graph? What's happening at the ends of the graph? And then, of course, we would want to discuss the number of turning points. Those are the small additions that we need to expand upon. So let's take a look at what this graph actually looks like. So this is what the graph of this is the same polynomial, looks like. So notice, I'll just kind of show some of the things. Here are my zeros, or my x-intercepts, at -1, 0, and +1. So the end behavior of the graph we can see as we go to the right, the graph points up. So to the right, the graph rises, and to the left, the graph rises. Okay, now notice at the intercepts. So notice we would consider this a touch. I'm going to put a T there. So and it's just a touch at that intercept because the graph comes down to -1 and then goes back up. When we get to 0, see how it's above 0 on the left and below 0 on the right. So we would consider that a cross. And then we would also consider it one across because it goes from below the x-axis to above. So in fact, this is determined by the multiplicity of the zeros. So just like we said above, for the 0, -1, if the graph touches, that's whenever the multiplicity is even. And we noticed that because we had a multiplicity of 2. So that implies that the graph will touch at that particular intercept. When we look at 0, x equals 0, again, the multiplicity would have to be odd because it crosses at 0. And again, notice up here, we had the x equals 0, we had an odd multiplicity of 3. So that told us that it would cross at 3. And then for 1, again, it would have to be odd, and we saw that, indicating that it would cross. So an even multiplicity implies that graph will touch at that intercept, while an odd implies it will cross. And so now let's think about the number of turning points. So when we consider the turning points, again, these are the max and the min. So I'm going to put a little x at the turning points. So this right here would be a turning point. This would be a turning point. Notice this doesn't change direction here. It's decreasing and decreasing, so that's not a turning point. But here it goes from decreasing to increasing, so this is a turning point. So there's 1, 2, 3 turning points. And what that does is it implies what the degree of the polynomial can be. So the degree of the polynomial will be at least the number of turning points plus 1. So since we have 3 turning points, the degree will be at least 3 plus 1, or 4, or even numbers beyond that. So 4, it could be 6, it could be 8. And notice that what did we say the degree was? The degree was 6. So let's dig a little bit deeper into the why behind some of these things. So to dig a little bit deeper, I want to talk about end behavior and power functions. Okay, so consider the following even power functions. So y equals x squared is considered a power function, a variable to a power. We would say this is even because the exponent is even. And we know what y equals x squared looks like. And we know what the behavior, the end behavior is, right? To the right, it rises. And to the left, the graph rises. Likewise, if we look at a negative even power function, such as negative x squared, and we know that that's a reflection about the x-axis. So to the right, this graph falls, and to the left, this graph falls. So now let's consider odd power functions similarly. So I'm going to think about x cubed. So we know what the graph of x cubed looks like. And in fact, with respect to end behavior, we would say to the right, it rises, the graph rises. And to the left, the graph falls. But when we look at the x-axis reflection, or negative x cubed, to the right, the graph falls, and to the left, the graph rises. So what's interesting is by keeping these four graphs in mind, which were parent functions that we've discussed in the past, this helps us determine the end behavior of more complicated polynomials. So a function with an even degree, like x squared, and a positive lead coefficient will have the same end behavior as y equals x squared. Likewise, a function with an even degree and a negative lead coefficient will have the same end behavior as y equals negative x squared. So for example, if I look at this polynomial function, so x to the fourth plus 3x cubed plus x squared minus 3x minus 2, again, focus on that lead term. So this is a degree 4 with a positive lead coefficient. So that means that, let's say degree 4 with a positive lead coefficient. So this is a positive even function, which means it will have the same end behavior as y equals x squared. And take a look at what the graph of this looks like. Both ends point up, just like x squared. Again, what goes on where the zeros are, whether they touch or cross, that's going to vary. But the end behavior will be just like f of x equals x squared. Likewise, if I'm looking at something with an odd degree, so consider negative x to the fifth minus 2x squared plus x. So what is the degree? So the degree is 5. We have a negative lead coefficient. So this is a negative odd function, odd powered function. And so in terms of end behavior, it's going to behave like y equals negative x cubed. So just like y equals negative x cubed, again, which we saw above, looks like this. The end behavior of this graph is consistent with that. To the right, it falls, and to the left, it rises. So now, when we're looking at a polynomial and we want to determine all of these things, we can do that. So let's take one last example to put this all together. So let's take f of x is equal to, how about negative 3x times x minus 1 squared times x plus 4. And let's think about some of these things. Okay, so first, let's find the zeros and their multiplicity. Okay, since this is given to us in factored form, I can identify the zeros by setting each factor equal to 0. So that means if negative 3x equals 0, then x equals 0. If x minus 1 equals 0, then x equals 1. And if x plus 4 equals 0, then x equals negative 4. So my zeros are x equals 0, and the multiplicity, remember, is the exponent associated with that 0. And since nothing's written there, it would be understood to be a 1, which is odd, which implies the graph will cross at that particular 0. X equals 1 has a multiplicity of 2, and that implies that the graph will touch at that particular 0, x equals 1. And then x equals -4 has a multiplicity of 1, again implying the graph will cross. So if we're talking about specifically x and y intercepts, I have found the x-intercepts 0, 0, 1, 0, and -4, 0. And if I replace 0, x with 0, we can see we would have 0 times 1 times 4, which is 0. And again, that gives me that same intercept I've already listed. So now let's think about the end behavior. So if we're talking end behavior, this is where I want to identify the degree and the sign of the lead coefficient. So the lead term, remember, we want to visualize this completely being multiplied out. So we would be multiplying a -3x to an x to the second power to an x to the first power. So that lead term would be -3. This would be 1 plus 2 is 3 plus 1 is 4, x to the fourth. So this is a negative even-powered function. So that means the end behavior will be similar to -x squared. So that implies, with respect to the end behavior, that to the right it falls, the graph falls, and to the left the graph falls. Okay, so then if we think about, we discussed turning points. So the maximum number of turning points is always going to be the degree minus 1. Notice when we were looking at the graph, we counted the turning points and added 1. So the degree we know is 4. So 4 minus 1 equals 3. So that means that the maximum number of turning points is either 3 or we go to the next smaller odd number of 1. All right, so let's sketch a graph. All right, so let's see. We have 0, 0, 1, 0, and then -4, 0. We know that the end behavior, both ends point down, so I would go to the rightmost x-intercept and point down, the leftmost x-intercept and point down. And so now let's consider the multiplicity of these zeros. So at -4, the multiplicity is 1, so that means it will cross. We don't know exactly how high it will go, but we need calculus for that. But we know eventually it'll come back down to pick up this x-intercept. And at 0, the multiplicity is 1, so it will cross. And again, we don't know how far it will dip down, but we know it will come back up. And then let's cross-check. At 1, it should touch 1, multiplicity of 2, and it touches, and it does. So again, this gives us the basics of this graph, that the ends point down, whether it touches or crosses at the x-intercepts. The exact height or depth of these local max and min, we don't know exactly yet. So again, you can see though where the turning points will be, right? So we would have a turning point here. We would have a turning point here where it changes direction from increasing to decreasing, from decreasing to increasing, and then again here from increasing to decreasing. And so you can see that that's consistent with what we talked about here, right? That there, we said the maximum number of turning points would be 3 or 1. And we can see in this case it is 3. And then again, when you're given the graph and you're predicting the degree, you can count the number of turning points and add 1. So the degree, again, would be 3 plus 1, which is 4. And then we would always say, or you go to the next even number, 6 or 8. Okay, let's stop there, and we will take a look at another example in another video.